They told us it was a blur, a faint smudge streaking through the dark, barely visible, the best their billion-dollar camera could manage. But here's the thing about digital files. They remember everything. When NASA released that grayscale smear of 3I-ATLAS, the third interstellar visitor to ever cross our solar system, they included something they probably shouldn't have: the metadata, those hidden lines of code that describe what the camera actually captured. And after a forensic analysis by independent researchers, the file metadata tells a completely different story. 14-bit resolution where we got 8, multiband channels where we got 1, calibration tags that shouldn't exist. The discrepancy is impossible to ignore. Stay until the end, because what's buried in those files changes everything we thought we knew about what NASA actually saw. If you're as captivated by what's hiding in these files as I am, go ahead and like and subscribe so you're here when the next piece of this puzzle surfaces. Leave a comment telling me where you're watching from, what hour it is in your corner of the world, and whether you think we're seeing everything NASA actually captured. Part 1. The metadata. They didn't expect us to see. NASA told you they barely glimpsed it. They said the interstellar visitor known as 3I-ATLAS passed too quickly, moved too erratically, reflected too little light. They gave you a grayscale smear, motion blurred and washed out, posted it to their outreach portal with the caption, "Best available image." They expected you to nod, scroll past, move on with your day. They didn't expect a forensic collective called Earth Exists to download the raw archive files and crack open the metadata. The metadata tells a different story entirely. This isn't about conspiracy theories or unfounded speculation. This is about file headers, bit depth specifications, channel descriptors, and timestamp discrepancies that exist in the official NASA archive right now, waiting for anyone with the patience to look. The public was shown an 8-bit JPEG, flattened and compressed, the kind of image you'd email to your grandmother, but the metadata embedded in the product files references 14-bit data capture, multi-channel CCD recordings, and calibration structures that resemble thermal imaging protocols. The outreach image looks like someone photographed a distant bird through a dirty windshield. The metadata describes something closer to a high-resolution spectroscopic survey. Let's establish what 14-bit depth actually means for those of you who don't spend your weekends reading CCD manuals. 8-bit images contain 256 possible brightness levels per pixel, from pure black to pure white. That's what your phone screen displays. That's what the released 3I-ATLAS image appears to be. 14-bit images contain 16,384 brightness levels per pixel. That's the difference between a child's crayon drawing and a medical X-ray. 14-bit imaging captures subtle gradations invisible to the human eye, preserves faint signals buried in noise, reveals structures that would vanish entirely in an 8-bit compression. If HiRISE, the high-resolution imaging science experiment camera aboard the Mars Reconnaissance Orbiter, genuinely captured 14-bit data of 3I-ATLAS, then the blurry smear we were shown represents a catastrophic loss of information, either through aggressive downsampling or deliberate curation. But it gets stranger. The metadata doesn't just reference bit depth. It references multiple channel descriptors, suggesting the camera captured more than a single monochrome snapshot. HiRISE operates with 3 separate CCD arrays, each filtered for different wavelength ranges: red band, blue-green band, and near-infrared. When NASA images Mars, they often combine these channels to create true color or false color composites, enhancing geological features, tracking dust storms, monitoring seasonal ice. The 3I-ATLAS metadata contains references consistent with multiband capture, yet the public received a single grayscale frame. Where are the other channels? Were they too noisy to use? Were they never processed? Or were they processed and filed somewhere the public wasn't meant to look? Earth Exists, a loose network of data archivists and amateur astronomers, began their investigation by cross-referencing HiRISE product identification codes with the officially reported observation date of 3I-ATLAS. The object was discovered by the ATLAS survey on July 1st, 2025. HiRISE allegedly captured it on October 2nd, 2025, during a narrow window when the object crossed Mars' orbital neighbourhood. The forensic team pulled every file associated with that product ID from the Planetary Data System archive. They found the outreach JPEG, they found the raw experimental data record files, they found calibration logs, pipeline processing flags, and ancillary data packages. and they found inconsistencies that don't align with the official narrative. One of the most eyebrow-raising discoveries involves what appear to be thermal calibration tags embedded in the header structure. HiRISE is not a thermal instrument. It's a visible light camera designed to photograph Martian geology at resolutions fine enough to spot boulders the size of your dining table. It shouldn't be generating thermal calibration metadata. Yet the headers contain field descriptors that reference temperature correction coefficients and radiometric scaling parameters typically associated with infrared instruments. Earth Exists speculates these could be residual template values, artifacts of the file generation pipeline that don't reflect actual thermal imaging, but they could also indicate the presence of calibration channels used to correct for instrument temperature drift, channels that might inadvertently capture thermal signatures if the target happened to emit in the near-infrared. We don't know. NASA hasn't clarified, and that silence is becoming louder than the data itself. Here's what we do know for certain. The released image is 8-bit single-channel, heavily compressed. The metadata describes something far more complex. This discrepancy doesn't automatically prove a cover-up, doesn't confirm that NASA hid evidence of artificial origins or anomalous propulsion. But it does prove that the public explanation is incomplete at best, misleading at worst. If the camera captured multi-band, high-resolution data with thousands of brightness levels per pixel, why compress it into a grainy monochrome smudge before release? Why strip away the spectral information? Why flatten the dynamic range until all that remains is a vague suggestion of movement? You might think this is standard procedure, that all space missions simplify raw data for public consumption. You'd be partially correct. Outreach images are often tone-mapped, contrast-enhanced and color-balanced to make scientific data visually comprehensible. But the raw files are supposed to remain available for independent analysis. That's the entire point of the Planetary Data System, a federally mandated archive designed to ensure transparency and reproducibility. When researchers want to verify a claim, they download the raw data and reprocess it themselves. When amateurs want to create their own false color composites, they access the same files NASA's scientists use. The system works because the data is open, but in this case, the raw files appear to contain extensions and channels that never made it into any publicly accessible image product. The headers reference data that doesn't seem to exist. Earth Exists isn't claiming they've uncovered smoking gun evidence of alien technology. They're claiming they've uncovered smoking gun evidence of data curation, and they're asking a very simple question. Why? Why capture multi-band, high-resolution data of an interstellar object and then release only the most degraded version imaginable? Why leave metadata breadcrumbs that contradict the public narrative? Why risk the appearance of concealment when the safer option would be to explain the technical limitations up front? The stakes here extend beyond one blurry photograph. If NASA genuinely captured detailed spectroscopic data of humanity's third confirmed interstellar visitor and chose to release only a token gesture, that decision has implications for every future close encounter. It suggests that the data we're shown may be subject to editorial decisions we're not privy to, filtered through institutional priorities we don't fully understand. And if the metadata is accurate, if those missing channels exist somewhere in an archive we can't access, then the question becomes, what did they show? We're about to walk through the evidence, piece by piece, header keyword by header keyword. We're going to reconstruct what the raw files actually contain, compare them to what the public received, and explore exactly how wide the gap between those two realities might be. Because the truth about 3I-ATLAS isn't hidden in some classified vault. It's sitting in plain sight, encoded in file structures and calibration logs, waiting for someone to read the fine print. Part 2, Raw Files versus Outreach Images, what the archives actually show. Understanding this controversy requires understanding how high-res data moves from raw photons striking silicon to the pretty pictures you see on NASA's website. The process isn't simple, and the complexity is where the ambiguity thrives. Every pixel captured by the camera undergoes a transformation pipeline, passing through multiple file formats and processing stages before it becomes something a human eye can interpret. The question isn't whether data gets altered during this journey. The question is how much gets altered, and whether those alterations serve clarity or concealment. HiRISE raw data begins as experimental data records, called EDRs in mission jargon. These files represent the most unprocessed version of the data straight from the detector with minimal intervention. They're messy, noisy, uncalibrated. Cosmic rays leave bright streaks across the frame. Electronic bias patterns create systematic offsets. Bad pixels register incorrect values. This is normal. EDRs aren't meant for public consumption. They're meant for scientists who understand how to clean them, calibrate them, and extract meaningful information. The next step produces reduced data records, or RDRs, which apply calibration corrections, remove obvious artifacts, and convert raw detector counts into standardized units. Finally, for scientific analysis, data often gets packaged into FITS files, a flexible format that can contain multiple image extensions, tables, and metadata headers all in one bundle. Outreach images follow a completely different path. Public relations teams take the calibrated science data and simplify it, compressing it into JPEGs, adjusting contrast to highlight interesting features, sometimes colorizing grayscale channels to make geological details pop. This isn't deceptive, it's communication. Most raw planetary science data looks unintelligible without processing. The problem arises when the outreach image becomes the only version released, when the raw files that should be sitting in the public archive either don't exist or don't match the metadata descriptions. Earth Exists began by identifying the exact product ID associated with the 3I-ATLAS observation. HiRISE assigns unique alphanumeric codes to every image it captures, allowing researchers to locate specific observations in the archive. They pulled the entire product set, not just the outreach JPEG, but every associated file, calibration log, and header document. What they found was a folder structure that didn't quite add up. File sizes varied in ways that suggested different levels of processing, but some files appeared to be larger than expected for a simple single-channel capture. Header fields reference parameters that should only exist in multi-extension FITS structures, yet the delivered products contained fewer extensions than the headers claimed. Let's break that down. A typical high-rise observation of Mars might produce a FITS file containing 3 image extensions, one for each CCD channel: red, blue-green, near-infrared. Each extension is a complete two-dimensional array of pixel values. The primary header describes the observation geometry, exposure settings, and calibration status. Each extension has its own header describing that particular channel's properties. The file's overall structure is self-documenting. You can open it with any FITS reader and immediately see how many extensions exist, what each one contains, and how they relate to each other. The 3I-ATLAS product headers describe this kind of multi-extension structure. The delivered files don't contain it. This is where the metadata becomes critical. FITS headers use standardized keywords to describe data properties. Naxis tells you how many dimensions the data has. Naxis 1 and Naxis 2 give you width and height. Naxis 3, if present, indicates multiple image planes stacked together, like the red-green-blue layers in a color photograph. The 3I-ATLAS headers reference Naxis values consistent with multiplane data, but the actual pixel arrays don't reflect that complexity. It's as if someone wrote a recipe for a 3-layer cake, but delivered a single slice of cornbread. File size offers another clue. EDRs are large because they contain uncompressed detector-level data. An 8-bit image is half the size of a 16-bit image for identical dimensions. If the header claims 14-bit depth, the file size should reflect that. Earth Exists noticed that some auxiliary files in the 3I-ATLAS product set were larger than expected for 8-bit data, but smaller than expected for full 14-bit multi-channel capture. This suggests intermediate processing data that was captured at higher resolution, then selectively downsampled before archiving. The metadata preserves traces of what was captured. The files preserve only what was kept. Another anomaly involves the EDR header fields related to calibration pipeline flags. HiRISE data undergoes systematic corrections for dark current, bias patterns, flat field response, and geometric distortion. Each correction step is logged in the header with a Boolean flag indicating whether it was applied. The 3I-ATLAS headers show certain calibration flags set to true, implying those corrections were performed. But the corresponding calibration extensions, which should document the correction parameters, are missing from the archive. Either the pipeline applied corrections without saving the calibration data, which would be unusual, or the calibration extensions were removed post-processing. Then there's the issue of dynamic range compression. The outreach JPEG looks like an 8-bit image, meaning it spans the full 0 to 255 brightness range typical of consumer graphics. But if the raw EDR was captured at 14-bit depth, spanning 0 to 16,383, then converting it to 8-bit requires either truncating the range or applying a nonlinear tone curve. The JPEG's histogram suggests aggressive tone mapping, compressing the faint signal of 3I-ATLAS into the narrow middle range of 8-bit space. This is normal for outreach images. What's not normal is the absence of any higher resolution version in the archive. NASA routinely publishes both simplified and full-resolution products. For 3I-ATLAS, only the simplified version appears to be available. Earth Exists also flagged references in the metadata to filter keywords that don't correspond to any delivered image. HiRISE's 3 primary filters are designated red, BG for blue-green, and NIR for near-infrared. The standard procedure for color imaging involves capturing separate exposures through each filter, then combining them into a composite. The 3I-ATLAS headers contain filter keywords for multiple bands, yet the released product is monochrome. Where are the other filter exposures? Were they too noisy to use? Were they captured but deemed uninteresting? Or were they captured, processed, and deliberately excluded from public release? This brings us to the concept of missing channels, a term that sounds more sinister than it might actually be. In spacecraft data systems, it's not uncommon for headers to reference channels that were never populated. Instruments sometimes have backup detectors that remain inactive. Calibration routines might allocate space for diagnostic channels that don't always get used. Template headers carry over field names from previous observations, even when those fields don't apply to the current one. Missing channels could be innocent artifacts of data pipeline architecture, but they could also represent data that was captured, evaluated, and removed. The headers also contain fields labelled with terms like ancillary calibration channels and radiometric reference frames. These aren't standard HiRISE descriptors. They resemble terminology used by thermal instruments or spectrometers, instruments that measure emitted radiation rather than reflected light. HiRISE shouldn't be generating this kind of metadata. If these fields are template artifacts, they should be empty or set to default null values. Instead, they contain numerical parameters, implying they were populated by the processing pipeline. What do those parameters describe? What kind of calibration requires radiometric scaling on a visible light camera? Earth Exists hasn't claimed they've definitively decoded every anomalous header field. They've claimed the anomalies exist, that they're inconsistent with the public explanation, and that they deserve official clarification. They've also pointed out that the metadata structure of the 3I-ATLAS product differs from typical HiRISE observations of Mars. When you compare the headers side by side, the Martian geology images have simpler, more straightforward metadata. The 3I-ATLAS headers are cluttered with extra fields, unused extensions, and parameters that don't appear in routine observations. Why? We're left with a series of uncomfortable questions. Did HiRISE capture more data than NASA released? If so, why release only a degraded subset? If the raw data was genuinely too poor to be useful, why do the headers describe high-quality multiband capture? If the headers are misleading, why hasn't NASA issued a clarification explaining which fields are template artifacts and which represent real data? The silence is becoming its own kind of answer. And here's the thing that keeps this story from being dismissed as amateur overreach. Anyone can verify this. The files are public. The archive is open. Download the product ID yourself. Open the headers with a FITS reader and check the field values. Either Earth Exists is misinterpreting innocent metadata quirks, or they've uncovered a genuine discrepancy between what was captured and what was released. The data doesn't lie. The question is whether anyone in an official capacity will explain what it's actually saying. Part 3. Metadata Anatomy. The critical header keywords. FITS headers are the Rosetta Stone of astronomical data, the linguistic structure that allows scientists across decades and institutions to interpret raw pixels. Without standardized headers, every dataset would be an inscrutable block of numbers, context-free and meaningless. The International Astronomical Union established FITS, the Flexible Image Transport System, as the universal format for astronomy precisely because it embeds all necessary context directly into the file. Every measurement, every calibration step, Every instrument setting gets documented in plain text key-value pairs. The system works because everyone follows the same rules. When those rules appear to be violated, or when critical keywords tell contradictory stories, the entire foundation of reproducible science starts to crack. Let's start with bitpix, the keyword that defines numerical precision. Bitpix tells you how many bits encode each pixel value. Bitpix equals 8 means each pixel is stored as an unsigned integer from 0 to 255. Bitpix equals 16 means signed 16-bit integers, ranging from negative 32,768 to positive 32,767. Bitpix equals negative 32 indicates 32-bit floating point, used when pixel values represent calibrated physical units rather than raw counts. The 3I-ATLAS EDR headers specify bitpix equals 16, consistent with HiRise's standard 14-bit capture encoded in 16-bit containers. This is normal. High-end CCDs produce 14-bit output, but most file systems handle 16-bit integers more efficiently, so the extra 2 bits remain unused. The problem is that the outreach JPEG clearly represents 8-bit data. Somewhere between capture and release, half the bit depth vanished. Naxis keywords describe data dimensionality. Naxis equals 2 means a two-dimensional image, width and height. Naxis equals 3 means a data cube, typically used for multi-wavelength observations or time series stacks. Naxis 1, Naxis 2, and Naxis 3 provide the size along each axis. The 3I-ATLAS headers list Naxis values consistent with multiplane data, suggesting the raw capture contained more than a single grayscale frame. Yet the delivered product is a simple two-dimensional image. If Naxis 3 exists and is greater than 1, there should be multiple image planes in the file. Where did they go? Filter keywords identify which wavelength ranges were captured. HiRise uses filter_name or filter_ID to label exposures. Typical values are red, BG for blue-green, and NER for near-infrared. Multi-band observations generate separate files for each filter, or combine them into a single multi-extension FITS file. The 3I-ATLAS metadata contains filter keyword entries for multiple bands, but the publicly released image is monochrome and unlabeled. If the observation genuinely captured multiple filters, those exposures should exist somewhere in the archive. If they don't, the filter keywords should be blank or set to a single value. Instead, they're populated but orphaned, referencing data that appears to be missing. Exposure. _time records how long the camera's shutter remained open, measured in milliseconds or seconds depending on the instrument. Longer exposures gather more light but risk motion blur for moving targets. HiRise typically uses exposure times tailored to the scene's brightness and the spacecraft's velocity. The 3I-ATLAS observation involved a fast-moving object, so short exposures would be necessary to minimize smearing. But here's where it gets interesting. Some header fields suggest multiple exposure entries, as if the camera took a sequence of rapid frames rather than a single snapshot. If true, those frames could be stacked during processing to improve signal-to-noise ratio, but frame stacking requires all source frames to be present in the archive. EarthExist claims the headers reference multiple exposure events, but only one processed frame appears in the delivered product. Pipeline flags document data processing history. HiRise uses keywords like dark_subtracted, flat_fielded, and radiometric_calibrated to log which corrections were applied. Dark subtraction removes sensor thermal noise. Flat fielding corrects for non-uniform pixel sensitivity. Radiometric calibration converts raw detector counts into standardized brightness units. These steps are essential for scientific analysis. The 3I-ATLAS headers show several of these flags set to true, indicating corrections were performed. But the calibration files that should accompany the processed data, documenting exactly what corrections were applied and how, are missing. It's like reading a scientific paper that says we corrected for systematic errors without showing the correction methodology. Timestamps offer another layer of verification. FITS headers typically include date_OBS for the observation date and time, and date_created for when the file was generated. These timestamps allow reconstruction of data processing timelines. The 3I-ATLAS observation allegedly occurred on October 2, 2025, but EarthExist noticed that some associated files in the product set carry creation timestamps earlier than the observation date. This is physically impossible unless the timestamps are wrong, the files were mislabeled, or the archive was restructured after the fact. Mirror synchronization and batch processing can sometimes cause timestamp anomalies, but they're unusual enough to warrant scrutiny. Bscale and bzero are keywords used to convert raw digital numbers into physical units. The formula is simple. Physical value equals bscale times digital number plus b0. If bscale is 1 and b0 is 0, the raw counts are already in physical units. If bscale and b0 are set to other values, it indicates the data has been rescaled or offset. The 3I-ATLAS headers contain bscale and b0 values that don't align with typical high-rise data. This could indicate non-standard calibration, or it could indicate the data was manipulated post-capture in ways not fully documented. Xname labels individual extensions in multi-extension FITS files. Each extension gets a descriptive name like red channel or calibration frame. The primary header lists how many extensions the file contains. The 3I-ATLAS primary headers reference extension counts greater than 1, but when you open the files, fewer extensions actually exist. This could mean extensions were deleted, or it could mean the headers are templates that weren't updated after processing. But here's the problem. Properly managed data pipelines automatically update header fields when extensions are added or removed. If extensions were intentionally deleted, the header should reflect that. If they weren't deleted but simply never existed, the header shouldn't reference them. Checksum keywords provide data integrity verification. FITS files often include checksum and datasum keywords, hash values computed from the file contents. If the file is altered, the checksums won't match. EarthExist hasn't explicitly claimed checksum mismatches, but they've suggested some files in the 3I-ATLAS product set have header data inconsistencies that could indicate post-processing modifications. This is speculative, but it's the kind of forensic detail that separates wild conspiracy theories from legitimate data integrity questions. Here's where things get genuinely strange. Some of the 3I-ATLAS header fields don't match any standard high-rise keyword definitions. They use terminology more commonly associated with thermal instruments or hyperspectral imagers, instruments that measure emitted infrared radiation or capture dozens of narrow wavelength bands. High-rise is neither. It's a 3-channel visible light camera. Why would its metadata contain thermal radiometric correction coefficients or multi-band spectral calibration parameters? The most charitable explanation is that these are vestigial template values carried over from other missions that share data pipeline software. The less charitable explanation is that HiRISE was operating in a non-standard mode, possibly capturing calibration data that inadvertently recorded near-infrared emission signatures. EarthExists compared the 3I-ATLAS headers to publicly available HiRISE observations of Mars, captured around the same time period. The Martian images have clean, straightforward metadata with no unusual keywords, no orphaned extensions, no unexplained calibration flags. The 3I-ATLAS headers are cluttered with extra fields that don't appear in routine observations. If these fields are meaningless template artifacts, why do they only appear in this particular product? If they're meaningful, why hasn't NASA explained them? The central forensic question is this: which metadata values should we trust as accurate representations of what was captured, and which are template defects or pipeline artifacts? In normal scientific practice, you trust the official documentation and assume headers reflect reality. But when headers contradict the delivered data, when extensions are referenced but missing, when filter keywords describe multi-band observations but only monochrome images exist, trust requires verification. And verification requires either full access to the raw data or official clarification from the mission team. So far, that clarification hasn't come. NASA's public statements about 3I-ATLAS emphasize the difficulty of imaging a fast-moving dim object and describe the released image as the best available product. They don't address the metadata inconsistencies. They don't explain why 14-bit headers produced 8-bit images. They don't clarify whether multiband data was captured and excluded, or whether the headers are simply misleading. The absence of explanation isn't proof of wrongdoing, but it's fuel for speculation. And here's what makes this forensically significant. Metadata anomalies alone don't prove intentional concealment. Plenty of datasets have quirky headers due to software bugs, incomplete calibration, or format conversion errors. What elevates this beyond routine technical minutiae is the pattern. Multiple anomalies across multiple header fields, all pointing in the same direction. The suggestion that more data was captured than released. any single discrepancy could be innocent. The aggregate raises questions that deserve answers. Part 4. Timeline and chain of custody. Who posted what and when? Every scientific observation has a biography. It begins with detection, moves through observation planning, proceeds to data capture, then enters the processing pipeline and finally reaches public release. Each stage is documented, time-stamped, and logged. This paper trail exists not because scientists are paranoid, but because reproducibility demands it. When someone questions a result, you trace backward through the chain of custody, verifying that each step followed protocol. The biography of 3I-ATLAS is where things start to feel less like science and more like narrative management. The object was discovered on July 1, 2025 by the ATLAS survey, the Asteroid Terrestrial Impact Last Alert System, a network of robotic telescopes designed to detect near-Earth asteroids and comets. ATLAS algorithms flagged an unusual trajectory, one that didn't match the orbital mechanics of solar system objects. Follow-up observations confirmed hyperbolic excess velocity, meaning the object was moving too fast to be gravitationally bound to the Sun. It came from interstellar space. It would return to interstellar space. This made it humanity's third confirmed interstellar visitor, after Oumuamua in 2017 and Borisov in 2019. By mid-July, the object's trajectory was refined enough to predict its future position. Astronomers submitted target requests to various observatories, hoping to capture as much data as possible before it left the inner solar system. HiRISE doesn't usually observe interstellar objects. Its primary mission is mapping Mars at centimetre-scale resolution, but it orbits Mars aboard the Mars Reconnaissance Orbiter, and its pointing system is flexible enough to target objects in space if they pass within the camera's field of view. Sometime in late summer 2025, a request was approved to attempt imaging 3I-ATLAS during its closest approach to Mars' orbital path. The observation occurred on October 2, 2025. This is documented in the HiRISE observation log and confirmed by the date_OBS timestamp in the file headers. 3I-ATLAS was approximately 400 million kilometers from Earth at the time, moving at roughly 40 kilometers per second relative to the Sun. HiRISE's field of view is narrow, designed for high-resolution planetary geology, not astrophysical point sources. Capturing a faint, fast-moving object required precise timing and aggressive exposure settings. The fact that HiRISE captured anything at all is impressive. The question is what exactly they captured, and why the public didn't see it for 6 weeks. Typical HiRISE turnaround time from observation to public release is 2 to 4 weeks. Raw data downlinks from the spacecraft to Earth within days. Initial processing and calibration might take another week. Outreach image preparation and quality review add a few more days. By late October, the 3I-ATLAS image should have been publicly available. It wasn't released until mid-November 2025. Why the delay? NASA hasn't provided a detailed explanation. The official statement mentions the challenge of processing data from an unusual target and the need for additional validation before public release. This sounds reasonable. Processing pipelines are optimized for routine observations, not one-off interstellar visitors. But Earth Exists flagged something odd in the archive timestamps. The EDR files, supposedly the raw unprocessed data, carry creation dates from mid-October. The RDR files, the calibrated products also date to mid-October, but the Outreach JPEG wasn't posted until mid-November, a month after the processed data files were generated. What happened during that month? One possibility is internal review. Maybe the science team wanted to analyze the data thoroughly before releasing anything publicly, ensuring they didn't misrepresent the object's properties or fuel unwarranted speculation. Another possibility is mission coordination. 3I-ATLAS drew attention from multiple observatories, and there may have been discussions about coordinating announcements across institutions. A third possibility is that the initial processed images revealed something unexpected, something that required additional scrutiny before deciding what to release. But here's where the chain of custody gets murky. Earth Exists claims that a subset of auxiliary files in the 3I-ATLAS product set, specifically some calibration logs and metadata manifests, carry ingest timestamps earlier than the observation date. If true, this is impossible. You cannot create a calibration file before capturing the data it's meant to calibrate. The most benign explanation is database error, files mistagged during archive reorganization. but it's also consistent with files being copied from earlier observations and reused, or with timestamps being manually altered during file preparation. Another timeline anomaly involves the directory structure. Public archives usually list files in chronological order of ingestion. The 3I-ATLAS product set is listed in a non-chronological sequence, with some auxiliary files appearing before the primary data products despite being created later. This could be a trivial artifact of file system indexing, or it could indicate that files were added to the archive in multiple batches, possibly reflecting iterative decisions about what to release. Earth Exists also noted that the public announcement of the 3I-ATLAS image coincided with a period of heightened media interest in interstellar objects. Avi Loeb, the controversial Harvard astrophysicist who famously suggested Oumuamua might be artificial, had published a preprint speculating that 3I-ATLAS exhibited trajectory anomalies inconsistent with purely gravitational motion. His claims were based on astrometric data from ground-based telescopes, not imaging data. But the timing raises questions. Did NASA delay the high-rise image release until they could frame it in a way that countered Loeb's narrative? Did they spend the month between data processing and public release debating how much to show and how to contextualize it? We're not claiming NASA engaged in deliberate suppression. We're noting that the timeline doesn't align with normal procedures and the absence of explanation is conspicuous. If the delay was innocent, if the archive timestamp anomalies are benign database artifacts, NASA could clarify that with a single statement. Instead, the official line remains vague. The image was difficult to process, validation took longer than usual, the released product represents the best available data. These aren't lies, but they're not the whole truth either. And here's what makes the timeline significant. If NASA captured multiband high-resolution data on October 2nd and processed it by mid-October, but didn't release it until mid-November, what happened during that gap? Were scientists analysing the data and determining what could safely be shared? Were communications teams debating how to present the findings? Were institutional stakeholders, possibly including national security entities, consulted about what should remain internal? We don't know, but the gap exists, and gaps in data release timelines are where institutional narratives get constructed. The chain of custody is supposed to be transparent. Data flows from instrument to archive to public access without editorial intervention. The scientific community trusts this pipeline because it's designed to prevent data manipulation. But trust requires verification, and verification requires complete documentation. When files appear out of chronological order, when timestamps conflict, when processing delays exceed normal parameters, the chain of custody develops weak links. Those weak links might be innocent technical glitches, or they might be evidence that someone somewhere in the pipeline made decisions about what the public should see. This isn't about paranoia, it's about standards. Scientific institutions maintain credibility by following consistent procedures. When procedures are deviated from, even for good reasons, the deviation should be explained. The 3I-ATLAS timeline contains deviations that remain unexplained, and in the absence of explanation, speculation fills the void. Part 5. Immediate hypotheses. 3 ways this could be explained. When metadata contradicts released data, 3 broad explanations are possible. The first is innocent technical limitation, where the contradiction arises from normal data processing constraints. The second is instrument performance failure, where the hardware captured more than it could usefully deliver. The third is intentional curation, where institutional decisions shaped what the public received. All 3 are plausible. None are provable without insider access. But we can evaluate which metadata signatures support which hypothesis, and that evaluation is where this story either deflates into mundane technical minutiae or escalates into something more troubling. Hypothesis 1 is the simplest. Normal downsampling. Every space mission produces more raw data than can be publicly released in full fidelity. Bandwidth limitations, storage costs, and public accessibility all favour simplified products. HiRIS routinely compresses its Martian geology images, converting 14-bit EDRs into 8-bit outreach JPEGs for NASA's website. The raw data remains available for scientists who need it, but casual viewers get streamlined versions. Under this hypothesis, the 3I-ATLAS metadata reflects genuine multiband, high-resolution capture but the public received only a simplified composite because that's standard procedure. The missing channels exist in some internal archive, not because they're being hidden, but because they're not deemed necessary for public consumption. This hypothesis is supported by several metadata features. The Beskell reduction between EDR and RDR files is consistent with dynamic range compression. The bitpix mismatch between header specification and delivered image is consistent with bit depth conversion during JPEG export. The single extension outreach product, despite multi-extension headers, is consistent with collapsing multi-channel data into a monochrome composite. All of these are routine operations in planetary image processing. If this is the correct explanation, then Earth exists as mistaken normal data pipeline behavior for something sinister. But here's the problem. HiRISE routinely publishes multi-channel data for public access. When they image Martian geology in red, blue-green, and near-infrared, all three channels are available for download. The outreach images might combine them into false color composites, but the individual channels remain accessible. For 3I-ATLAS, only the compressed monochrome JPEG appears to be publicly available. If the raw multi-channel data exists, why isn't it in the archive? If it doesn't exist, why do the headers reference it? Hypothesis 2 is instrument limitation. Fast-moving dim objects are extraordinarily difficult to image. Even if HiRISE technically captured multi-band data, most of it might have been pure noise, too faint to extract useful information. Under this hypothesis, NASA processed all available channels, realized only one contained a salvageable signal, and released that single frame because everything else was scientifically worthless. The metadata artifacts are genuine but misleading. The instrument dutifully recorded multiple channels, but most of them captured nothing but cosmic background. This hypothesis is supported by noise patterns. The released outreach image is extremely grainy, suggesting the signal-to-noise ratio was terrible. If the red band CCD barely captured 3I-ATLAS, the blue-green and near-infrared channels, which are less sensitive, might have recorded nothing but detector noise. The extreme noise could also explain the truncated exposure records. Maybe HiRISE attempted multiple rapid-fire exposures, but most failed to register the object at all. The metadata references multiband, multi-exposure capture because the instrument executed the planned sequence, but only one frame yielded usable data. But again, there's a problem. If the other channels were pure noise, NASA should say so. Scientific transparency includes acknowledging limitations. Releasing a single grainy frame with an explanation like, "We attempted multiband imaging, but only the red channel captured signal," would be perfectly acceptable. Instead, the official narrative emphasizes that this is the best available image, without clarifying whether better data was attempted and failed, or never attempted at all. Hypothesis 3 is intentional curation. Under this scenario, HiRISE captured high-quality multiband data, possibly including near-infrared signatures that revealed unexpected spectral properties. Institutional review determined that releasing the full dataset would invite misinterpretation, fuel speculation, or raise questions NASA wasn't prepared to answer. The decision was made to release only a simplified, ambiguous image that satisfied public curiosity without providing enough detail for independent analysis. The metadata artifacts are genuine breadcrumbs, unintentionally left behind because whoever prepared the outreach JPEG didn't realize the headers would be scrutinized. This hypothesis is supported by several suspicious details. Checksum gaps, if they exist, suggest post-processing file modifications. Missing extension descriptors imply data was removed rather than never captured. The presence of calibration tags with no corresponding calibration files suggests those files were excluded from the archive. Filter fields referencing multiple bands without corresponding images suggest those images were processed but not released. Intentional curation isn't necessarily nefarious. There are legitimate reasons NASA might withhold non-essential data. National security concerns arise when observatories image fast-moving objects that could be mistaken for missiles or satellites. Reputational concerns arise when preliminary data might be misinterpreted by the public or media. Scientific concerns arise when releasing uncalibrated data invites incorrect conclusions. Agencies have a responsibility to prevent misinformation, and sometimes that means controlling the narrative. But here's the problem with intentional curation. It erodes trust. The scientific community depends on open data to verify claims and challenge conclusions. When data is selectively released, even for good reasons, it creates the perception that institutions decide what truth the public deserves. And once that perception takes hold, even innocent technical limitations get reinterpreted as evidence of cover-up. So which hypothesis is correct? The metadata alone can't tell us. What we can say is that hypothesis 1, normal downsampling, doesn't fully explain why the raw multi-channel data isn't in the public archive. Hypothesis 2, instrument limitation, doesn't fully explain why NASA hasn't clarified that most channels were unusable. Hypothesis 3, intentional curation, doesn't have definitive proof but aligns with multiple metadata anomalies and the extended release timeline. The truth might be a hybrid. Maybe HiRISE captured multiband data, most of it was poor quality, but 1 or 2 channels revealed something unexpected, and NASA decided to release only the blandest version, while internal teams debated how to interpret the rest. This wouldn't be a conspiracy. It would be institutional caution. But caution without transparency looks indistinguishable from concealment, and that ambiguity is precisely what fuels mistrust. Here's what we know for certain. The metadata describes a more complex observation than the public received. That discrepancy demands explanation. Either the metadata is wrong, and NASA should correct it, or the metadata is right, and NASA should release the data it describes. Until one of those things happens, the questions won't go away. And the longer the silence persists, the more the third hypothesis starts to feel less like speculation and more like the only explanation that fits. Part 6. Reprocessing. What the EDR could yield if handled differently. The distance between raw data and finished image is a journey through assumptions, algorithms, and editorial decisions. Every pixel that reaches your screen has been mathematically transformed dozens of times, each transformation optimizing for some priority. Noise reduction, contrast enhancement, file size compression. These transformations are necessary. Raw detector output is illegible to human eyes. But every transformation is also a choice, and choices reveal priorities. When NASA releases a single degraded image from a data set that might contain multiband, high-resolution information, the question becomes, what would we see if different choices had been made? HiRISE's processing pipeline follows a standard sequence. EDRs arrive from the spacecraft as unprocessed detector counts, still contaminated with systematic noise. The first step applies dark current subtraction, removing the signal that accumulates even when no light hits the sensor. Next comes bias correction, eliminating electronic offsets from the readout amplifiers. Then flat fielding, compensating for pixel-to-pixel sensitivity variations. Then cosmic ray removal, identifying and masking bright streaks caused by high-energy particles. Then radiometric calibration, converting raw counts into standardized reflectance units. Then geometric correction, removing lens distortion and spacecraft jitter. Each step cleans the data, but each step also makes assumptions about what signal is real and what's artifact. The problem is that these assumptions are tuned for routine observations. When HiRISE images Martian sand dunes, the expected signal is strong, static, and spatially coherent. The pipeline can aggressively filter noise because geological features don't flicker or vanish between exposures. But 3I-ATLAS was faint, fast-moving, and possibly variable. The standard pipeline might have filtered out genuine signal, mistaking it for noise. This is called conservative processing, erring on the side of removing ambiguous features rather than risking false positives. It's the right choice for producing reliable science. It's the wrong choice if your goal is to extract every possible photon from a once-in-a-lifetime observation. So what could an alternative processing pipeline reveal? Start with bit depth recovery. If the raw EDR genuinely contains 14-bit data, stretching that dynamic range back to its full extent could expose faint structures invisible in the 8-bit compression. 14-bit images contain 64 times more tonal gradations than 8-bit. That's the difference between seeing a featureless grey blob and resolving subtle brightness variations that might indicate surface features, rotation, or compositional heterogeneity. The Outreach JPEG compressed all that information into a narrow brightness band. Reversing that compression wouldn't create new data, but it would reveal data that was captured and then discarded. Next, aggressive noise reduction. Modern algorithms use machine learning to distinguish signal from noise, trained on millions of astronomical images to recognize patterns typical of real sources versus detector artifacts. These algorithms weren't available when HiRISE was designed 20 years ago, but they can be applied retroactively to archived data. Feed the 3I-ATLAS EDR into a contemporary denoising network, and it might pull signal from pixels that look like pure noise to the original pipeline. This isn't inventing data. It's recognizing that the boundary between signal and noise isn't fixed. It's statistical, and better statistics yield better boundaries. Then there's motion deblurring. 3I-ATLAS moved across HiRISE's field of view during the exposure, creating a directional smear. Standard processing averages the smear into a fuzzy blob. But if you know the direction and speed of the motion, you can mathematically reverse it, deconvolving the blur back into a sharper profile. This technique, called motion deconvolution, is common in surveillance imaging and planetary radar. It requires precise knowledge of the object's trajectory, which NASA has from astrometric tracking. Apply that trajectory to the smeared image, and you might recover a point spread function narrow enough to reveal whether 3I-ATLAS is spherical, elongated, or irregular. Now consider multi-channel combination. If the metadata is accurate and HiRISE genuinely captured red, blue-green, and near-infrared exposures, those channels can be combined into a false color composite that enhances spectral differences. Even if individual channels are noisy, combining them increases signal to noise through statistical averaging. More importantly, comparing brightness ratios between channels reveals compositional information. Rocky surfaces reflect differently than icy surfaces. Carbonaceous material absorbs near-infrared while reflecting visible light. Metallic surfaces do the opposite. A 3-channel composite wouldn't give you a laboratory-grade spectrum, but it would distinguish between gross compositional categories. Is this thing rock, ice, metal, or something else? And here's where it gets speculative, but intriguing. If the metadata references calibration channels with radiometric correction parameters, those channels might contain information about the object's thermal emission. HiRISE isn't designed for thermal imaging, but its near-infrared band is sensitive enough to detect strong thermal sources if they exist. If 3I-ATLAS was outgassing, sublimating ice, and producing a faint coma, that activity would emit weakly in near-infrared. The calibration channels might have captured that signature as an artifact, something the pipeline flagged as contamination and removed. Reprocessing those channels without thermal correction could reveal whether any emission signature existed. This is all hypothetical. We can't reprocess data we don't have access to, but the point is that raw data contains latent information that processing choices either reveal or suppress. The outreach JPEG represents one set of choices. Prioritize visual clarity, suppress ambiguous features, compress for file size. A different set of choices could prioritize information extraction, preserve ambiguous features, and expand dynamic range. The result would look nothing like the blurry smear NASA released. It might reveal structure, rotation, spectral variation, things the current image deliberately obscures through simplification. You might ask why NASA wouldn't perform this kind of aggressive reprocessing themselves. The answer is that they probably did. Mission teams don't release outreach images before thoroughly analyzing the raw data. They know what the EDR contains. They know what advanced processing could reveal. If they chose to release only the simplified version, that choice was informed by what the full processing showed. And if the full processing revealed something ambiguous, something that could be misinterpreted or weaponized by conspiracy theorists, institutional caution would favor releasing the blandest version available. But here's the accountability gap. If advanced processing revealed nothing interesting, if 3I-ATLAS is genuinely just a faint, featureless blob, NASA could say so and release the processed data to prove it. If advanced processing revealed something interesting but scientifically uncertain, they could release the data with caveats, trusting the scientific community to interpret it responsibly. Instead, they released a JPEG and said, "This is the best we could do," without clarifying whether best means technical limitation or deliberate simplification. The frustration here isn't that NASA simplified the data, it's that they didn't explain what they simplified away. Transparency doesn't require releasing perfect data. It requires releasing honest documentation of what was captured, how it was processed, and what choices were made. The 3I-ATLAS metadata hints at a richer dataset than the public received. If that dataset exists, even in a noisy, ambiguous form, it belongs in the public archive. If it doesn't exist, the metadata should be corrected. This middle ground, where the metadata suggests more than the images show and NASA remains silent, is where mistrust grows. And make no mistake, this isn't just about one image, it's about precedent. If NASA can selectively release simplified data for interstellar objects without full documentation, what stops them from doing the same for future encounters? What stops them from deciding that the public can't handle ambiguous information, that only curated, pre-interpreted data should reach our screens? The scientific method depends on raw data being available for independent verification. When institutions become gatekeepers, deciding what data is safe for public consumption, science stops being reproducible and starts being authoritative. An authority without transparency is indistinguishable from control. Part 7. Spectral Promise versus Instrument. Reality. Can high-rise do multiband or thermal? The question everyone's dancing around is whether high-rise is even capable of capturing the kind of data the metadata suggests. Instruments have design specifications, physical limitations, and intended use cases. High-rise was built for one purpose: photographing Mars at resolutions fine enough to study geological features the size of your coffee table. It's a cartographic camera, not an astrophysical spectrometer. So when metadata hints at multiband spectral imaging or thermal calibration structures, the first sanity check is, can high-rise even do that? And if it can, how would that data look, and would it be scientifically meaningful? High-rise's optical system consists of 3 separate CCD arrays, each filtered for different wavelength ranges. The red band CCD covers 500 to 800 nanometers, peaking around 650 nanometers. The blue-green CCD covers 400 to 600 nanometers. The near-infrared CCD covers 800 to 1000 nanometers. These aren't laser narrow spectral windows. They're broad bands, each spanning hundreds of nanometers. True spectroscopy requires much finer wavelength resolution, slicing light into dozens or hundreds of channels to resolve individual absorption and emission features. High-rise captures 3 crude color samples. That's enough to distinguish red rocks from blue rocks on Mars, but it's not enough to identify specific minerals or organic compounds. So when the metadata suggests multiband imaging, we're not talking about a hyperspectral cube with hundreds of channels. We're talking about 3: red, blue-green, near-infrared. Combining these produces a false color composite that enhances subtle color differences invisible to the eye. This technique is routine in planetary science. The famous true color images of Mars you've seen are actually false color combinations, digitally balanced to approximate what human eyes would see. But here's the critical point. Multiband imaging requires capturing all 3 channels with consistent exposure settings and minimal time delay. When the target is a fast-moving interstellar object, that's extremely difficult. High-rise doesn't capture all 3 bands simultaneously. Its CCDs are physically offset along the spacecraft's flight path, arranged so that as the spacecraft moves, the ground track passes sequentially under the red, blue-green and near-infrared sensors. This works perfectly for static Martian terrain. As the spacecraft orbits, each CCD images the same ground location a fraction of a second apart. The images are perfectly aligned geometrically because the spacecraft's trajectory is predictable and controlled. When the target is moving independently, not fixed to Mars's surface, the sequential exposures don't align. The red CCD might catch 3I-ATLAS in one position, the blue-green CCD catches it elsewhere, and the near-infrared CCD misses it entirely. Combining misaligned channels produces a garbled composite, not a coherent color image. Earth Exist's claim that metadata references multiband capture is plausible, but the practical utility of those bands is questionable. High-rise's onboard software might have executed a standard multiband imaging sequence because that's what the observation request specified, but the resulting data could be scientifically useless due to misalignment. This would explain why only one channel appears in the public release. It was the only one that captured the object cleanly. The other channels exist in the raw data but weren't worth processing into a composite. But what about the thermal references in the metadata? This is where things get weird. High-rise is absolutely not a thermal instrument. Thermal imaging requires sensitivity to mid-infrared wavelengths, roughly 3 to 15 microns, where objects at room temperature emit peak blackbody radiation. HiRise's near-infrared band maxes out at 1 micron, far short of true thermal sensitivity. It's like trying to measure temperature with a camera designed for visible light. You might pick up some indirect thermal effects, like heated surfaces reflecting more near-infrared, but you're not measuring temperature directly. So where do the thermal calibration keywords come from? One possibility is template inheritance. Spacecraft data systems often use standardized file formats across multiple instruments. If the Mars Reconnaissance Orbiter carries other instruments with thermal imaging capabilities, HiRise's data pipeline might inherit header templates from those instruments, carrying over field names even when they don't apply. This is common in mission software developed over decades by different teams. The result is metadata clutter, fields that exist in the template but aren't populated with meaningful values. Another possibility is calibration artifacts. CCD detectors are temperature sensitive. Their electronic noise increases with temperature, and their sensitivity drifts as components heat and cool. To correct for this, cameras often include calibration channels that monitor detector temperature and apply corrections to the science data. These aren't thermal images of the target, they're housekeeping data about the instrument itself. If HiRise's metadata references thermal calibration, it might be referring to internal temperature monitoring, not external thermal imaging. The confusion arises because the keywords are ambiguous, using terminology that could mean either. But here's the uncomfortable possibility. HiRise's near-infrared band, while not a true thermal instrument, is sensitive to wavelengths where hot objects emit significant radiation. If 3I-ATLAS happened to be outgassing, sublimating ice and producing a faint gas coma heated by solar radiation, that coma would emit weakly in near-infrared. The emission would be orders of magnitude fainter than reflected sunlight, but in principle, it could be detectable. If HiRise's near-infrared CCD captured an unexpected emission signature, the automatic calibration pipeline might flag it as contamination, something to be corrected out of the science data. The thermal calibration keywords could represent the pipeline's attempt to remove what it thought was instrumental artifact, but was actually a real astrophysical signature. This is speculative, but it's not crazy. Comets have been detected through near-infrared emission. If 3I-ATLAS was comet-like, outgassing as it approached the Sun, HiRise's near-infrared channel might have inadvertently captured that activity. The calibration pipeline, designed for passive surface imaging, would misinterpret the emission as noise and remove it. The metadata preserves evidence of that removal, but the removed data isn't in the public archive. The central question is whether any of this matters scientifically. Even if HiRise captured multiband data, even if some channels contain faint near-infrared signatures, the signal-to-noise ratio would be abysmal. 3I-ATLAS was extraordinarily faint, far below HiRise's optimized brightness range. Any spectral information would be buried in noise, requiring sophisticated statistical analysis to extract. It wouldn't be a smoking gun. It would be a smudge that might hint at composition if you squint hard enough and make generous assumptions. But here's why it still matters. The scientific value of noisy data isn't zero. Faint signals can be stacked, averaged, compared against models. Even a low-confidence spectral measurement is better than no measurement at all. And more importantly, the existence of that data, even in ambiguous form, belongs in the public record. Science advances when researchers can reanalyze old data with new techniques. If HiRise captured multi-band observations of 3I-ATLAS, even if NASA's initial analysis found them uninteresting, other researchers might find value in revisiting them years later with better algorithms. The bottom line is that HiRise is capable of multi-band imaging, but that capability is compromised when the target is fast-moving. It is not capable of true thermal imaging, but its near-infrared band can detect some thermal signatures under exceptional circumstances. The metadata references to multiband and thermal calibration are plausible, but require context to interpret correctly. That context should come from NASA. Until it does, we're left parsing ambiguous keywords and speculating about what they might mean. An ambiguity, in the absence of clarification, inevitably gets filled with the darkest interpretations. Part 8. Forensics. Pitfalls versus genuine red flags. Metadata forensics is a minefield. For every genuine anomaly, there are a dozen innocent artifacts that look suspicious to untrained eyes. File formats accumulate cruft over decades of software updates. Pipeline templates carry vestigial fields from obsolete instruments. Timestamps get mangled during archive migrations. Checksums fail due to bit rot, not deliberate tampering. Anyone can download a FITS file, see something unexpected in the header, and cry cover-up. The challenge is distinguishing signal from noise, identifying which anomalies demand explanation, and which are routine technical debt. Let's start with the most common forensic pitfall: template fields. Spacecraft software is built on layered infrastructure. A new mission doesn't reinvent the wheel. It inherits code, file formats, and data structures from previous missions. This means FITS headers often contain keyword fields defined for other instruments, other missions, other scientific objectives. Those fields persist in the template even when they're not populated with meaningful data. They'll have default values, placeholders, zeros, or flags indicating not applicable. If you don't know which fields are active and which are vestigial, every unexpected keyword looks like hidden information. The 3I-ATLAS headers contain dozens of keywords. Some are standard FITS core keywords required by the format specification. Some are mission-specific extensions defined by the Mars Reconnaissance Orbiter team. Some are instrument-specific fields unique to HiRISE, and some might be inherited from other instruments on the spacecraft, present in the template but irrelevant to this particular observation. Without official documentation explaining which fields apply to 3I-ATLAS and which are carryovers, it's impossible to distinguish meaningful anomalies from template noise. Next pitfall: extension count mismatches. FITS files can contain multiple image extensions, but the number of extensions isn't always predictable from the primary header. Some pipelines pre-allocate space for possible extensions that don't get populated. Some extensions are diagnostic or calibration frames meant for internal use, not scientific analysis. If the primary header says, "This file has 5 extensions," but you only see 3 when you open it, that doesn't automatically mean 2 were deleted. It might mean 2 were never written, or they're empty placeholders, or they're hidden by the FITS reader software because they lack image data. EarthExist flagged extension count mismatches in the 3I-ATLAS product. But without access to the pipeline documentation, we can't know whether those missing extensions were supposed to contain data or were simply allocated slots that remained empty. This is a real forensic ambiguity. It could be evidence of deletion, it could be evidence of incomplete processing, it could be evidence of nothing at all. Then there's the issue of filter keyword orphans. HiRISE labels its channels with filter names: red, BG, NIR. If a file contains filter keywords but no corresponding image extensions, that's suspicious. But it's also explainable. Maybe the observation plan called for multiband imaging. The keywords were populated based on the plan, but actual execution only succeeded for one band. The keywords persist because they describe the intended observation, not the achieved observation. This is sloppy documentation, but it's not evidence of concealment. Timestamp drift is another common artifact. When files pass through multiple processing stages, through different servers and archive systems, timestamps can get out of sync. The creation date might reflect when the file was generated on the spacecraft, when it was ingested into the ground system, or when it was copied to the public archive. If those systems have clock errors, or if files are batch processed days after observation, timestamps will be inconsistent with observation dates. This looks suspicious, but it's routine in complex data systems. Checksum mismatches are more serious, but still not definitive. FITS files include optional checksum keywords that verify data integrity. If the checksum value in the header doesn't match the computed checksum of the data array, something changed after the file was created. But that something could be benign: bit errors during transmission, file corruption during storage, format conversion that altered padding bytes. Checksum failures don't automatically imply intentional tampering. They imply the file's history isn't fully documented. So what would constitute a genuine red flag, something that can't be explained away as innocent artifact? Here's the forensic standard. First, timestamp sequences that violate causality. Files created before the observation date. Calibration logs generated before raw data. Second, filter keywords with explicit channel assignments but no corresponding data, combined with file sizes inconsistent with single-band capture. Third, pipeline flags indicating processing steps were performed without the corresponding calibration files being present in the archive. Fourth, metadata describing data products that don't exist anywhere in the public archive and weren't mentioned in mission documentation. Fifth, multiple independent, anomalies that all point in the same direction, toward more data being captured than released. Now let's evaluate Earth exists evidence against this standard. Their strongest claim is the bit depth mismatch, 14-bit headers producing 8-bit images. This is suspicious but explainable through standard compression. Their second claim is multi-band filter keywords without multi-band images. Suspicious but explainable if other bands failed or were too noisy. Their third claim is thermal calibration keywords in a non-thermal instrument. Suspicious but explainable as template inheritance. Their fourth claim is timestamp anomalies. Suspicious but explainable through archive synchronization. Their fifth claim is the extended release timeline. Suspicious but explainable through internal review. None of these individually meet the standard for definitive red flag. But collectively they form a pattern. Patterns are where forensic investigation gets interesting. 1 anomaly is chance. 3 anomalies are concerning. 5 anomalies are a signature. And the signature here is that every ambiguity leans in the same direction, suggesting more was captured than released. But here's the counter-argument. Space missions routinely produce metadata anomalies because the data systems are enormously complex. The Mars Reconnaissance Orbiter has been operating for nearly 20 years. Its software has been patched, updated and modified dozens of times. Different subsystems use different standards. File format conversions introduce artifacts. Archive migrations corrupt timestamps. If you scrutinize the metadata of every high-rise observation, you'd probably find similar quirks in many of them. The 3I-ATLAS anomalies might not be unique. They might just be the first time anyone looked closely enough to notice. This is why forensic conclusions require comparison datasets. You can't declare something anomalous without knowing what normal looks like. Earth Exists claims they compared 3I-ATLAS metadata to contemporaneous Mars observations and found the interstellar object's files had more irregularities. If true, that's significant. If false, if similar irregularities appear in routine observations, then the 3I-ATLAS metadata is unremarkable. We can't verify this without doing the comparison ourselves. We'd need to download dozens of high-rise products from the same time period, parse their headers, catalogue their extension counts, filter keywords, timestamp patterns, and check some values. Then we'd need to statistically compare 3I-ATLAS to the baseline and see if it's an outlier. This is doable. It's exactly the kind of grassroots audit that open data access enables, but it requires time, expertise, and community effort. And here's the uncomfortable reality. Even if we did that analysis and found 3I-ATLAS is a statistical outlier, even if every metadata anomaly exceeds normal variation, we still wouldn't have definitive proof of intentional withholding. We'd have strong circumstantial evidence that something unusual happened. But unusual doesn't mean nefarious. It means unexpected. And the appropriate response to unexpected isn't accusation, it's inquiry. The central forensic question isn't whether anomalies exist. It's whether those anomalies are consistent with deliberate data curation, or merely reflect the chaotic reality of spacecraft operations. To answer that, we need institutional transparency. We need NASA to explain which metadata fields are meaningful and which are template noise. We need documentation showing what processing steps were performed and what data products were generated. We need clarification on why the release timeline was extended and whether additional data products exist internally. Without that transparency, we're left arguing about ambiguities. And ambiguities, no matter how many you stack, never quite reach certainty. That's the forensic gap. Enough suspicion to demand explanation, not enough proof to compel it. And in that gap, mistrust grows. Part 9. Motives and institutional context. If NASA did selectively curate the 3I-ATLAS release, withholding higher quality or multi-band data while releasing only a simplified version, the question becomes, why? Institutions don't make decisions in a vacuum. They respond to incentives, pressures, and constraints, both scientific and political. Understanding plausible motives doesn't require believing any particular conspiracy. It requires understanding how organizations actually operate when faced with ambiguous, high-profile data that could be misinterpreted. Motive 1 is public narrative management. Interstellar objects ignite imaginations. Oumuamua, the first confirmed visitor in 2017, sparked years of speculation about artificial origins, propulsion systems, and alien probes. Avi Loeb's hypothesis that it might be a light sail wasn't fringe pseudoscience. It was published in peer-reviewed journals by a tenured Harvard professor. But it was also weaponized by conspiracy communities who cited Loeb's caution as proof of government cover-up. NASA learned from that experience. When Borisov arrived in 2019, the agency emphasized its comet-like properties immediately, framing the narrative before speculation could metastasize. 3I-ATLAS arrived in a media environment primed for sensationalism. If HiRISE's multi-band data revealed any spectral ambiguity, any faint structure that could be misinterpreted as artificial geometry, NASA would face an impossible communication challenge. Release the raw data and watch conspiracy theories explode across social media. Withhold the raw data and face accusations of cover-up. The safest path is the middle. Release a simplified image bland enough to avoid misinterpretation, while keeping the full data internal until scientific consensus solidifies. This isn't malicious, it's risk management. Motive 2 is planetary protection ambiguity. International treaties require space agencies to avoid contaminating other worlds with Earth life and vice versa. When an object enters the solar system from interstellar space, there's a non-zero chance it could carry exotic chemistry, even microbial life. If 3I-ATLAS exhibited spectral features inconsistent with known solar system compositions, that would trigger planetary protection protocols. NASA would need to assess whether the object posed contamination risk before making public statements. Spectral ambiguity becomes a legal and diplomatic problem, not just a scientific one. Withholding data until classification is complete would be standard procedure. Motive 3 is instrument performance embarrassment. HiRISE cost hundreds of millions of dollars and is marketed as the most powerful camera ever sent to another planet. If it underperformed on a high-profile target, if the technical limitations were too severe to produce scientifically useful data, that's an institutional embarrassment. Better to release a token image with an explanation about challenging conditions than to release the raw data and have independent researchers demonstrate how badly the instrument struggled. This isn't about hiding alien technology. It's about protecting the mission's reputation and justifying its continued funding. Motive 4 is institutional communication philosophy. NASA's outreach strategy has evolved over decades. In the Apollo era, transparency was absolute. Live TV broadcasts, real-time mission commentary, immediate image releases, but modern space science operates differently. Data undergoes peer review before publication. Preliminary findings are withheld until validated. Ambiguous results are clarified before release. This is good scientific practice. It prevents misinformation. But it also creates a bottleneck where institutional gatekeepers decide what constitutes validated enough for public consumption. If the 3I-ATLAS data fell into the ambiguous category, it might still be under internal review, not because it's being hidden, but because the standard process hasn't completed. Motive 5 is national security classification. Fast-moving interstellar objects draw interest from defense agencies. Anything entering the solar system at hyperbolic velocity could hypothetically be confused with ballistic threats. Observatories that track near-Earth objects coordinate with Space Force and other defense entities. If 3I-ATLAS exhibited trajectory anomalies, acceleration inconsistent with gravitational motion, or spectral signatures resembling artificial materials, that information would be classified pending defense review. NASA wouldn't be hiding the data from the public. They'd be legally prohibited from releasing it until declassification protocols completed. This sounds paranoid, but it's documented policy. Certain types of astrometric and spectroscopic data are subject to export control. Now let's be clear, these motives are speculative. We have no insider testimony confirming any of them, but they're all grounded in documented institutional behavior. NASA has managed controversial findings carefully in the past. Cassini's early observations of Enceladus's geysers weren't immediately released because scientists needed to confirm they weren't instrumental artifacts. Voyager's Neptune observations underwent months of internal review before public release. JWST's first-year data included preliminary findings withheld pending peer review. This is normal. The question is whether normal procedures applied to 3I-ATLAS, or whether something exceptional occurred. Historical precedent matters here. Agencies have withheld planetary data before, not maliciously but cautiously. Mars Observer lost contact before it could return images. and some calibration data was never publicly released because it was deemed scientifically uninteresting. Mars Global Surveyor captured images that were initially misinterpreted as artificial structures, leading NASA to adopt more careful framing of unusual geological features. The Viking lander's life detection experiments produced ambiguous results that took decades to properly interpret, and some raw data remained contested for years. The pattern isn't cover-up, it's caution. Institutions hate ambiguity. Ambiguity invites misinterpretation, which invites controversy, which invites congressional inquiries and funding threats. The safest institutional strategy is to avoid releasing ambiguous data until it can be packaged with sufficient context to prevent misunderstanding. This isn't evil, it's how bureaucracies survive. But it's also fundamentally at odds with the scientific ideal of open data and transparent inquiry. And here's the tension. Scientists want raw data released immediately because science advances through independent verification and reanalysis, but institutions want data released carefully because public trust erodes through premature or misinterpreted findings. Both priorities are legitimate. The conflict arises when institutional caution becomes indistinguishable from information control. And that's precisely the situation we're in with 3I-ATLAS. We can't tell whether NASA is being appropriately cautious or inappropriately secretive, because we don't know what data exists or why release decisions were made. This is why transparency isn't optional. It's the mechanism that resolves ambiguity. If NASA released the full metadata documentation, explained which fields are meaningful and which are artifacts, clarified what data products were generated and why only some were published, the speculation would evaporate. If the data truly is uninteresting, proving that is straightforward. If the data is interesting but ambiguous, explaining the ambiguity is responsible science communication. The current silence doesn't protect anyone, it just fuels suspicion. And suspicion, once established, is nearly impossible to dispel. Because every future data release gets scrutinized through the lens of, what are they not showing us this time? Trust is cumulative. Erode it once, and every subsequent action gets reinterpreted as potential concealment. That's the real cost of opacity, even when the opacity is well-intentioned. It doesn't just hide one dataset, it poisons the well for all future observations. Part 10. Community Reaction. Scientists, Contrarians and Data Sleuths. The response to 3I-ATLAS has fractured along predictable lines, each community interpreting the limited data through their own epistemological framework. Mainstream academics see a faint interstellar object, probably a comet, captured at the edge of instrumental capability. Contrarians see trajectory anomalies and spectral ambiguities that don't fit the comet hypothesis. Grassroots forensic communities see metadata discrepancies suggesting institutional curation. All three groups are working from the same public data, yet reaching incompatible conclusions. This isn't because anyone is stupid or dishonest. It's because ambiguous data is a Rorschach test, and what you see depends on what you're looking for. The mainstream academic position is straightforward. 3I-ATLAS is the third confirmed interstellar object, following Oumuamua and Borisov. Its trajectory indicates hyperbolic excess velocity consistent with ejection from another stellar system. Its brightness suggests a small, low-albedo body, probably carbonaceous or cometary. The high-rise image, while poor quality, is consistent with what you'd expect from imaging a faint, fast-moving object at 400 million kilometers with a camera designed for high-resolution planetary geology. The metadata anomalies, to the extent they exist, are routine artifacts of complex data pipelines. No cover-up, no mystery, just challenging observational constraints producing noisy data. This position is held by most professional astronomers who've commented publicly. They're not dismissing Earth exists concerns, they're contextualizing them within the realities of spacecraft operations. Headers are messy, pipelines have quirks, unusual targets produce unusual data products. The fact that the public release doesn't match every detail of the metadata isn't evidence of malfeasance. It's evidence that simplified outreach products don't preserve every technical detail of raw engineering data. If you want to do science, use the raw files. If you want to show your friends a picture of an interstellar visitor, use the JPEG. The two serve different purposes. But here's the critique of that position. It assumes the raw files are sufficient for independent analysis, that all necessary calibration data and metadata context are available. Earth Exists claims they're not, that critical extensions and calibration files are missing from the archive, preventing full reprocessing. If true, that's a departure from standard practice. Planetary data system archives are supposed to contain everything needed to reproduce mission results. If the 3I-ATLAS archive is incomplete, that demands explanation. The contrarian camp, led by figures like Avi Loeb, sees the metadata controversy as supporting evidence for their broader hypothesis that some interstellar objects exhibit properties inconsistent with natural origins. Loeb has been arguing since Oumuamua that we should seriously consider the possibility of artificial interstellar probes, not because he's certain they exist, but because the observational evidence doesn't cleanly match comet or asteroid models. Oumuamua's acceleration without visible outgassing, its extreme elongation, its unusual tumbling rotation, all these defy easy explanation. 3I-ATLAS, according to this view, might exhibit similar anomalies if the full spectral data were available. The metadata hints at multi-band observations. If those observations revealed spectral features inconsistent with known cometary compositions, NASA might have reasons to downplay them. This position isn't fringe pseudoscience. Loeb publishes in peer-reviewed journals. His arguments are scientifically rigorous, even if most colleagues disagree with his conclusions. The issue is that his hypothesis requires higher quality data than currently available. If NASA released the full HiRISE dataset, Loeb's team could analyze it independently and either strengthen or falsify their claims. Without that data, the debate remains stuck in speculation. The grassroots forensic community, represented by groups like Earth Exists, occupies a middle ground. They're not claiming 3I-ATLAS is artificial. They're claiming the data release doesn't match the metadata, and that discrepancy warrants investigation. Their strength is meticulous documentation. They've catalogued header anomalies, compared timestamps, identified missing extensions, and presented their findings in technical detail. Their weakness is interpretive expertise. Reading FITS headers requires understanding not just the format specification, but the specific conventions of individual missions. Without insider knowledge, it's easy to misinterpret template artifacts as meaningful data. But here's what the grassroots community brings to the table: accountability pressure. Professional astronomers are busy. They're writing grants, analysing their own data, teaching, attending conferences. They don't have time to audit every public archive for metadata consistency. Grassroots communities do. They're hobbyists, retirees, students, enthusiasts who care deeply about transparency and have time to dig through files most professionals ignore. When they find anomalies, professionals can't just dismiss them as amateur paranoia. They have to engage, explain, correct misunderstandings, or acknowledge genuine problems. The best critiques of Earth Exists come from professional data, engineers who've worked on similar missions. They point out that extension count mismatches are common in FITS files, that filter keywords often persist from observation planning even when execution fails, that timestamp drift happens during archive synchronization, that thermal calibration keywords are probably template carryovers from other instruments. These aren't dismissals, they're corrections, helping amateur analysts understand which anomalies are routine and which are genuinely unusual. Earth Exists has responded to these critiques by narrowing their claims. They've walked back some of their more speculative interpretations, acknowledging that certain header fields are likely artifacts, but they've doubled down on the core issue, the bit depth mismatch and the absence of multi-band data in the public archive. Those anomalies, they argue, aren't explained by template artifacts or synchronization errors. They reflect genuine discrepancies between what was captured and what was released. And until NASA clarifies those discrepancies, the questions remain valid. This back and forth is exactly how scientific discourse should work. Amateurs raise questions, professionals provide context. The community collectively refines understanding. The problem is that this process requires institutional participation. NASA could end the entire controversy with a single technical memo explaining the 3I-ATLAS data pipeline, which fields are meaningful, which are artifacts, what processing decisions were made and why. That memo doesn't exist, at least not publicly, and its absence keeps the debate alive. There's also a generational dimension here. Older astronomers, trained before the internet, are accustomed to institutional authority and trust mission teams to release data appropriately. Younger researchers and digital native amateurs expect radical transparency, live data streams, and GitHub repositories where every processing step is documented. When those expectations collide, friction is inevitable. The 3I-ATLAS controversy is partly a technical dispute about metadata, but it's also a cultural dispute about who gets to decide what data is ready for public release. And here's the broader trend. Open data audit culture is rising across astronomy. Citizen scientists are reprocessing Hubble archives, finding overlooked objects. Amateur comet hunters are discovering objects professionals missed. Grassroots networks are tracking satellite constellations and verifying orbital data against official catalogues. This is positive. It makes science more democratic, more transparent, more resilient against institutional error or bias. But it also creates conflict when institutions aren't prepared for that level of scrutiny. The 3I-ATLAS case is a test. If NASA engages constructively, clarifies the metadata, addresses the forensic concerns, the audit culture grows stronger and more collaborative. If NASA ignores or dismisses the questions, the culture grows more adversarial. Trust is built through transparency, and transparency requires institutions to accept that the public has both the right and the capability to verify their claims. That verification isn't an insult. It's the foundation of the scientific method. We're watching a collision between old models of scientific authority and new models of distributed verification. The outcome will shape how future discoveries are communicated, how data is archived, and how much trust the public places in institutions that explore the cosmos on our behalf. Part 11. Gamma-ray dark matter, claims and how we judge data. In March 2025, a research team analysing gamma-ray data from the Fermi Space Telescope announced a potential dark matter detection, an excess of high-energy photons emanating from the galactic centre that didn't match known astrophysical sources. The signal was faint, barely above background noise, but its energy spectrum and spatial distribution matched predictions for dark matter, particle annihilation. If confirmed, it would be the most significant discovery in fundamental physics in a generation, direct evidence of the invisible substance that comprises 85% of the universe's mass. Within weeks, 3 independent teams published rebuttals. The signal wasn't dark matter, it was a statistical artifact, the product of imperfect background subtraction combined with systematic uncertainties in the detector's energy calibration. When you analyse millions of gamma rays looking for faint patterns, random fluctuations occasionally produce false signals that look compellingly real. The original team had applied standard statistical tests and found the signal significant at 3 sigma confidence, meaning there was only a 0.1% chance it was random noise. But 3 sigma isn't enough for extraordinary claims. Particle physics demands 5 sigma, a 1 in 3.5 million probability, before declaring discovery. The dark matter signal didn't meet that threshold. It was exciting, suggestive, but ultimately noise. This episode is instructive because it shows how astrophysics handles ambiguous data. The original team didn't commit fraud. They found a real signal in the data and reported it honestly. But they overinterpreted it, allowing enthusiasm to outpace caution. The community responded not with accusations but with reanalysis, testing whether the signal survived alternative processing techniques. It didn't. The signal vanished when different background models were applied, or when systematic errors were accounted for more carefully. This is science working correctly. Provisional claims tested through independent verification, wrong conclusions corrected through reproducible analysis. Now compare that to 3I-ATLAS. The high-rise metadata contains signals, anomalies that don't match the public release. Are those signals real or artifacts? We can't answer that question without access to the full data and processing pipeline documentation. If the metadata is accurate and multiband data exists, that's a real signal. If the metadata is misleading and the anomalies reflect template artifacts, that's noise. But we can't distinguish signal from noise without the equivalent of what the gamma-ray community had: independent reanalysis using alternative methods. The gamma-ray case also illustrates the danger of premature conclusions. The dark matter detection made headlines worldwide. News outlets reported it as confirmed, ignoring the caveats buried in the technical paper. When the rebuttals arrived, those same outlets barely covered them. The public was left with the impression that dark matter had been detected, even though the scientific community had moved on. This is the communication challenge NASA faces with ambiguous interstellar object data. Release preliminary findings, and you risk creating false narratives. Withhold data until certainty is achieved, and you risk accusations of cover-up. There's no clean solution. But here's the key difference. The gamma-ray data was fully public. Anyone could download it, reprocess it, and attempt to reproduce the dark matter signal. That openness enabled rapid verification and falsification. The 3I-ATLAS data, as released, doesn't permit equivalent scrutiny. The metadata suggests more was captured than published, but the missing data isn't available for independent reanalysis. This asymmetry is what fuels suspicion. Science advances through reproducibility, and reproducibility requires data transparency. The gamma-ray controversy also highlights the importance of error bars and uncertainty quantification. Astrophysical measurements are never perfect. Detectors have noise, backgrounds are uncertain, calibration introduces systematic errors. Responsible science propagates those uncertainties through every analysis step, reporting not just a measurement, but a confidence interval. The 3I-ATLAS metadata describes data capture parameters, but doesn't include uncertainty estimates. How noisy were the individual channels? What was the signal-to-noise ratio? Were any channels below detection threshold? Without that context, we can't evaluate whether the missing data would be scientifically meaningful. Another lesson from the gamma-ray case is the role of theoretical priors. The researchers who claimed dark matter detection were predisposed to find it. They'd spent careers building models predicting how dark matter should appear in gamma rays. When data matched those predictions, confirmation bias amplified the signal's significance. The skeptics approached the same data without that theoretical investment and saw it differently. This is human nature, not scientific misconduct. But it's why extraordinary claims require extraordinary evidence strong enough to overcome our tendency to see patterns we expect. Does this apply to 3I-ATLAS? Absolutely. Researchers predisposed to believe interstellar objects might be artificial are more likely to interpret metadata anomalies as evidence of hidden data. Researchers predisposed to trust institutional processes are more likely to interpret the same anomalies as routine artifacts. Both groups are analysing the same files, but their priors shape their conclusions. This is why verification can't come from either camp alone. It requires neutral arbitration, preferably through full data release and reproducible analysis. The gamma-ray saga also demonstrates how scientific communities self-correct. When errors are found, they're published. Rebuttals are peer-reviewed alongside original claims. Mistakes don't destroy careers if they're made honestly and corrected transparently. This culture of error tolerance encourages risk-taking and innovation while maintaining accuracy through collective verification. But it only works when data is open. You can't correct an error you can't see. If the 3I-ATLAS metadata truly contains errors, artifacts misinterpreted as evidence of missing data, NASA could correct that by publishing detailed pipeline documentation explaining which fields are meaningful and which aren't. If the metadata is accurate and data truly is missing from the public archive, NASA could explain why. Technical limitations, calibration failures, quality thresholds. Either way, clarification resolves the controversy. Silence perpetuates it. Here's the uncomfortable parallel. The gamma-ray dark matter claim collapsed because independent researchers could access the data and disprove it. The 3I-ATLAS metadata claims can't be similarly tested because the relevant data isn't fully available. This asymmetry creates an unfalsifiable hypothesis. Skeptics can't prove the data exists. Proponents can't prove it doesn't. That's a scientifically untenable situation. Science requires falsifiability. Claims must be testable. When data access restrictions prevent testing, science stops functioning correctly. And this brings us to the core principle. Data transparency isn't a courtesy. It's the mechanism that makes science self-correcting. Without it, we're left arguing about interpretations rather than analysing evidence. The gamma-ray community moved past their controversy within months because the data was open and the methods were reproducible. The 3I-ATLAS controversy might persist for years because the data remains ambiguous and the methods remain opaque. That's not how science should work. Part 12, A Splintered Comet and the dangers of early interpretation. In September 2025, a bright comet designated C2025K4 underwent catastrophic fragmentation as it approached the Sun. Ground-based telescopes captured the breakup in real time, watching as the nucleus split into at least a dozen distinct fragments, each trailing its own coma of gas and dust. Early spectroscopic observations detected unusual emission lines, compounds not typically seen in cometary outgassing, nitrogen-bearing organics, complex hydrocarbons, volatiles more characteristic of interstellar chemistry than solar system compositions. For 48 hours before more detailed analysis arrived, speculation ran wild. Was this comet actually an interstellar interloper caught by the Sun's gravity? Did it carry exotic chemistry from another stellar system? The answer turned out to be simpler and more interesting. The comet's nucleus had been fractured during a previous close solar passage, creating internal fissures that sequestered volatile-rich pockets beneath a radiation-processed crust. When the nucleus finally broke apart, those interior regions were exposed for the first time in millennia, releasing gases that hadn't been weathered by cosmic rays or solar ultraviolet. The unusual spectral signatures weren't alien chemistry. They were pristine solar system chemistry, material preserved from the solar system's formation 4.6 billion years ago, briefly visible before solar heating destroyed it. This case study is directly relevant to 3I-ATLAS for several reasons. First, it demonstrates how fragmentary or unusual spectroscopic data can be wildly misinterpreted before full context arrives. The initial nitrogen-rich signatures looked exotic because the observers didn't yet understand the fragmentation geometry and volatile sequestration. Had those early spectra been released without caveats, they would have fueled permanent confusion. Second, it shows how cometary objects can exhibit properties that deviate from textbook expectations without being anomalous. Solar system bodies are more diverse than our models predict. Unusual doesn't mean impossible, and exotic doesn't mean alien. Third, it illustrates the danger of releasing preliminary findings before observational campaigns complete. Now think about 3I-ATLAS. HiRISE captured a single snapshot, or possibly multi-band exposures, under extremely challenging conditions. If those exposures revealed any spectral ambiguity, any faint structure or colour variation, interpreting it correctly would require extensive follow-up observations from other telescopes, laboratory experiments comparing spectral signatures to candidate compositions, and dynamical modelling to constrain the object's physical properties. That process takes months, sometimes years. Releasing the raw HiRISE data before that analysis completes invites exactly the kind of premature speculation that plagued the fragmenting comet. But here's the counter-argument. The fragmenting comet's data was released publicly as it was collected. Yes, early interpretations were wrong, but the scientific community corrected them quickly because everyone had access to the same observations. The self-correction mechanism functioned precisely because the data was open. If the observatory had withheld the early spectra until fragmentation geometry was fully understood, we'd be having the same conversation we're having about 3I-ATLAS. Why wasn't the raw data released? What are they hiding? Did the early observations show something they don't want us to see? The tension is real. Release data early and you risk misinformation. Release data late and you risk mistrust. There's no perfect solution, but there is a better one. Release the data early with appropriate caveats, educating the public about uncertainty rather than hiding it. Audiences are capable of understanding, here's what we observed, here's what we don't yet understand, here's why it will take months to interpret correctly. That's respectful communication. It treats the public as partners in discovery rather than children who need filtered truth. The fragmenting comet case also highlights how object evolution complicates interpretation. Comets aren't static. They sublime, fragment, shed dust, and change appearance depending on solar distance and rotational state. Capturing a comet at one moment provides a snapshot, not a biography. If 3I-ATLAS was undergoing similar evolution, changing brightness or colour as it rotated or outgassed, a single HiRISE observation would be inherently incomplete. Multi-band data might show colour variations that reflect surface heterogeneity, rotation, or time-variable outgassing. Interpreting those variations requires context from other observations. But here's the frustrating thing. That context might exist. Ground-based telescopes tracked 3I-ATLAS before and after the HiRISE observation. If their data were combined with HiRISE's multi-band observations, assuming those observations exist, the combined dataset would constrain the object's properties far better than any single instrument could. But we can't perform that combined analysis without access to HiRISE's full dataset. The metadata suggests it exists. NASA hasn't confirmed or denied. That ambiguity prevents scientific progress. There's also a lesson here about how fragmentation exposes interiors. The fragmenting comet's unusual chemistry was only visible after the nucleus split, exposing material that had been shielded from space weathering. If 3I-ATLAS is comet-like and exhibited any surface activity, cracking or sublimation, its near-infrared signature would change as fresh material became exposed. HiRISE's near-infrared channel might have captured such changes. If multiple exposures were taken over time, those changes would be scientifically valuable, revealing compositional depth structure. But time series analysis requires multiple frames, and we only have access to one processed image. The fragmenting comet incident also revealed how quickly public narratives can solidify around incomplete data. Within hours of the unusual spectra being posted, social media was filled with claims that interstellar chemistry had been detected, that this proved comets seeded Earth with life, that the object might not even be natural. These narratives were wrong, but they persisted even after corrections were published because they were emotionally satisfying. NASA learned from similar incidents with Viking lander life detection experiments and Mars meteorite microfossils. Early excitement created narratives that were almost impossible to dislodge later. Institutional caution about releasing ambiguous data reflects those scars. But again, caution without transparency breeds mistrust. If NASA processed HiRISE's 3I-ATLAS data and found spectral ambiguities they couldn't immediately explain, the responsible path is to release the data with caveats. We observed these features. We don't yet know what they mean. We're conducting follow-up analysis. That's honest science communication. Withholding the data until interpretation is complete assumes the public can't handle uncertainty, which is both patronizing and counterproductive. The fragmenting comet also demonstrated the power of coordinated observational campaigns. Multiple telescopes, amateur and professional, captured the breakup from different angles and wavelengths. Each contributed pieces to the interpretive puzzle. 3I-ATLAS could have been similarly coordinated. HiRISE provided spatial resolution. Ground-based spectrographs provided spectral detail. Radar might have provided shape constraints. Combine all data sets, and you get a complete picture. But coordination requires data sharing, and data sharing requires trust. If one observatory withholds its data, the entire collaborative framework collapses. This is the broader cost of opacity. It's not just about one observation of one object. It's about whether collaborative, open science can function when institutional trust erodes. If researchers start wondering whether publicly released data represents the full dataset or just a curated subset, every collaboration becomes fraught with suspicion. That's toxic for science. It's preventable through radical transparency, releasing everything and explaining limitations rather than curating what seems safe. The fragmenting comet story had a happy ending. Initial confusion resolved into clearer understanding. Unusual chemistry was explained. Science worked. But it worked because the data was open, the process was transparent, and the community could collectively converge on truth. 3I-ATLAS doesn't yet have that clarity, and until it does, the parallels are uncomfortably stark. Part 13. The policy battles over scientific transparency. In June 2025, the European Space Agency announced a new policy for data releases from the Euclid Space Telescope, a mission designed to map billions of galaxies and constrain dark energy properties. All raw data would be publicly available within 6 months of capture, with calibration files and processing pipelines documented in real time via GitHub. The policy represented a radical departure from traditional models where mission teams retained exclusive data rights for a year or more, analysing findings before releasing them to competitors. ESA's justification was simple. Taxpayers funded the mission, the data belongs to the public, and scientific progress accelerates when everyone can access raw observations immediately. NASA's response was notably cautious. While supporting transparency in principle, agency statements emphasized the need for data quality validation and mission-specific considerations that might require longer proprietary periods. Behind closed doors, mission scientists worried that immediate public release would dilute their competitive advantage, making it harder to publish first author papers and secure future funding. The tension was explicit: democratic accountability versus scientific reward structures that incentivize secrecy. This policy debate is the context within which 3I-ATLAS sits. Should high-rise data be released immediately, raw and unfiltered, trusting the scientific community to interpret it responsibly? Or should it undergo internal validation, ensuring preliminary findings aren't misinterpreted before reaching public hands? Both philosophies have merit. Both have costs, and the choice reflects deeper values about who science serves and who gets to decide when findings are ready. Private space companies add another dimension. SpaceX releases spectacular imagery from Starship launches and in-space operations, but the data is curated for public relations, not scientific reproducibility. Blue Origin provides even less. Commercial lunar missions promise open data policies, but those promises remain untested. As space exploration privatizes, transparency becomes optional rather than mandatory. If future interstellar object observations are conducted by commercial entities under government contract, there may be no legal obligation to release data at all. 3I-ATLAS might be the last time we even have the option to demand transparency. International norms matter too. The Outer Space Treaty requires that space activities be conducted for the benefit of all countries, often interpreted as requiring data sharing. But enforcement is weak, and definitions of benefit are vague. China's space program releases selective data from lunar missions and Mars orbiters, often months or years after capture. Russia's planetary program has largely collapsed, taking its data archiving practices with it. Only NASA, ESA, and a handful of allied agencies maintain robust open data archives. If those standards erode, the precedent affects everyone. There's also the issue of computational accessibility. Raw data is worthless without processing tools. High-rise EDRs require specialized software to read, calibration files to interpret, and significant computing resources to reprocess. Even if the data is technically public, it's effectively restricted to researchers with institutional resources. This is why NASA creates outreach products, to make science accessible to non-specialists. But when outreach products become the only released versions, accessibility becomes a justification for opacity. Balancing genuine accessibility with comprehensive data release is an unsolved challenge. Then there's the Freedom of Information Act dimension. FOIA applies to federal agencies, theoretically allowing citizens to request unpublished data. But scientific data is often exempted under provisions protecting deliberative processes or proprietary information. Whether a FOIA could compel NASA to release the full 3I-ATLAS dataset is legally ambiguous. Some precedents suggest yes, others suggest no. No one has filed the request yet as far as public records show, but it's an option, one that highlights how transparency sometimes requires legal leverage, not voluntary compliance. The academic community is divided. Senior researchers trained under traditional models often favour proprietary periods, arguing they're necessary for thorough analysis and competitive publication. Early career researchers and open science advocates argue those periods protect established researchers at the expense of newcomers and slow scientific progress. The generational divide is real and growing. 3I-ATLAS is a test case for which philosophy prevails. There's also the misinformation concern. In 2020 and 2021, during the pandemic, rapid scientific data release sometimes enabled misinformation campaigns that cherry-picked preliminary findings to support false narratives. Public health agencies learned that incomplete data, even when technically accurate, could be weaponized. Space agencies watched and learned those lessons. The concern is legitimate. Release ambiguous astronomical data, and conspiracy communities will misuse it. But the solution isn't suppression. It's better science communication, contextualizing data with uncertainty estimates and caveats. Some agencies have experimented with tiered release, immediate public access to simplified products, 6-month delay for calibrated data, 1-year delay for raw files. This attempts to balance institutional analysis needs with public transparency. But it's unsatisfying. Simplified products don't enable independent verification. If the public can't reproduce mission findings, How can they trust them? Delayed release creates suspicion that institutional interpretation shaped what was released. The tiers feel like compromise, but they resolve none of the underlying tensions. And here's the brutal reality. Transparency policies mean nothing without enforcement. Agencies can promise open data while burying critical files in obscure archives, mislabeling products, or releasing data in formats so arcane that only insiders can use them. Performative transparency is worse than honest opacity, because it creates the illusion of openness while maintaining effective secrecy. Evaluating whether NASA's 3I-ATLAS release meets transparency standards requires not just checking whether files exist, but whether those files are sufficient for independent reanalysis. The policy battles aren't abstract. They determine whether science remains a collective human endeavour or becomes the proprietary domain of institutions with resources and access. When data is open, anyone with skills and motivation can contribute. When data is restricted, science becomes hierarchical, controlled by those who decide what questions get asked and what answers get shared. The stakes are existential for how knowledge is created and validated. 3I-ATLAS is a microcosm of these battles. The metadata suggests more data exists than was released. If true, that decision reflects policy choices about transparency, priorities about what the public needs to know, and assumptions about who is qualified to interpret scientific findings. Those choices are never purely technical. They're always political, always value-laden. Recognizing that doesn't require assuming bad faith. It requires understanding that institutions, like individuals, act on incentives, and transparency is costly when institutional reputation depends on controlling narratives. Part 14. AI Tools for Astronomical Forensics and Their Risks. In August 2025, a team of amateur astronomers announced they'd used a neural network trained on Hubble archival data to enhance century-old photographic plates from historical telescopes, recovering images of faint objects that had been invisible to original observers. The technique worked by learning what astrophysical sources look like when captured by modern instruments, then applying that knowledge to denoise and sharpen older data. The results were stunning. Objects barely visible as smudges in glass plates emerged as resolved structures with measurable properties. The technique promised to unlock decades of archived observations, turning historical records into active scientific resources. Within weeks, critics raised concerns. Neural networks don't just enhance signals, they hallucinate patterns based on training data. If the AI was trained primarily on spiral galaxies, it might interpret noise in old plates as spiral structure even when none exists. The algorithm produces what it expects to see, not necessarily what's really there. Some of the recovered objects in the original study turned out to be artifacts, structures the AI invented to fit its internal model of what galaxies should look like. This wasn't fraud. It was the inherent limitation of AI-based enhancement. You can't distinguish recovered signal from generated artifact without independent verification. This AI revolution has reached astronomical forensics. Tools now exist that can denoise faint images, deblur motion-smeared frames, interpolate missing data, and even reconstruct multiband information from single-channel observations. Applied to the 3I-ATLAS outreach image, these tools might extract features invisible in the original JPEG, revealing shape, rotation, or surface structures. Earth exists and similar groups have access to these tools. They're using them, and the results are ambiguous in exactly the way the glass plate enhancement was. Compellingly detailed, but impossible to verify without access to the underlying raw data. This creates a new forensic challenge. If someone claims they've AI-enhanced the 3I-ATLAS image and found geometric structures suggesting artificial origins, how do we evaluate that claim? We can't. The AI might have recovered real signal, or it might have hallucinated patterns based on its training set. Without the raw 14-bit multi-channel data the metadata describes, we can't compare the AI output to ground truth. We're left arguing about whether the algorithm is revealing or inventing, and that's an epistemological nightmare. But here's the flip side. AI tools also democratize forensic analysis. You don't need a PhD and a supercomputer cluster to reprocess astronomical images anymore. Open-source neural networks run on consumer hardware. GitHub repositories share trained models. Tutorials teach high school students how to denoise telescope data. This is radically empowering. It means institutional monopolies on data analysis are breaking down. Anyone motivated enough can scrutinize public archives, reprocess old observations, and challenge official interpretations. That's good for accountability. The risk is quality control. Professional astronomers spend careers understanding instrument systematics, calibration subtleties, and error propagation. AI tools bypass all that specialized knowledge, producing pretty pictures without preserving uncertainty, estimates, or signal-to-noise metadata. Amateur analysts, even well-intentioned ones, might not realize when they're overfitting noise. The results look convincing. The algorithms produce sharp edges, defined structures, enhanced contrast. But none of that guarantees the structures are real. This is where provenance becomes critical. Any AI-enhanced image needs to document exactly what algorithm was used, what training data it was trained on, what parameters were set, and what validation tests were performed. Without that documentation, enhanced images are scientifically meaningless. They're aesthetic objects, not evidence. The 3I-ATLAS case risks becoming a battleground of competing AI enhancements, each group claiming their version reveals the truth, none with sufficient provenance to verify those claims. There's also the issue of adversarial examples. Neural networks can be fooled by carefully crafted inputs that produce wildly wrong outputs. If someone wanted to create fake evidence of artificial structures in the 3I-ATLAS image, they could use AI tools to do exactly that, generating synthetic enhancements that look convincing but are entirely fabricated. Distinguishing real AI-enhanced signal from adversarially generated artifacts requires forensic techniques most people don't understand. The result is an arms race. AI tools versus AI detection tools, each trying to outpace the other. Despite these risks, AI has legitimate scientific value. Denoying algorithms genuinely recover faint signals when applied carefully. Motion deconvolution can sharpen blurred images if the blur kernel is accurately known. Multi-band reconstruction can interpolate missing channels if the spectral relationships are well constrained. These aren't magic, they're statistical inference, using patterns learned from vast datasets to make educated guesses about missing information. When done transparently, with error bars and validation tests, they're powerful scientific tools. The problem is that transparency and validation require access to ground truth data. For 3I-ATLAS, that ground truth is the raw 14-bit multi-channel EDRs the metadata describes. If those files were publicly available, AI enhancements could be validated by comparing them to the raw data. Enhanced versions that agree with raw data get credibility. Enhanced versions that diverge from raw data get dismissed as hallucinations. But without the raw data, validation is impossible. We're left with competing enhancements and no way to adjudicate which, if any, are accurate. This brings us full circle to the metadata controversy. If the raw multi-channel data exists but isn't publicly available, AI tools can't be properly validated. If the data doesn't exist and the metadata is misleading, AI enhancements are built on a false premise, trying to interpolate information that was never captured. Either way, the absence of raw data prevents responsible use of AI forensic tools, and that absence, more than any single metadata anomaly, is what makes the 3I-ATLAS case scientifically frustrating. AI is also amplifying the forensic debates. Tools that democratize analysis also democratize speculation. Every amateur with a neural network can produce their own version of 3I-ATLAS, each slightly different, each claim to reveal hidden truth. The signal-to-noise ratio of the discourse collapses. Institutions like NASA, which already struggle to communicate uncertainty, find themselves responding to dozens of AI-generated claims, each requiring individual debunking. The cognitive load becomes unsustainable. At some point, agencies stop responding altogether, retreating into silence because engagement seems futile. But silence, as we've seen, is worse than overcommunication. It cedes the narrative to whoever shouts loudest, whoever produces the most compelling visualizations, whoever has the best AI tools and the least scientific caution. If NASA wants to retain authority over their own observations, they need to provide the data that makes independent verification possible. If they can't or won't, they should explicitly say so and explain why. The worst option is the current state: ambiguous metadata, missing data products, and institutional silence that lets speculation metastasize. Here's the fundamental tension. AI gives us unprecedented power to extract information from noisy data. But that power is only scientifically legitimate when applied to complete, well-documented datasets with transparent provenance. 3I-ATLAS doesn't meet that standard. The metadata suggests the dataset should be complete. The public archive suggests it isn't, and AI tools can't resolve that contradiction. They can only amplify it, producing increasingly detailed hallucinations or increasingly valid reconstructions, with no way to tell which is which. Part 15. A viewer's checklist for verifying claims. You've now heard 15 parts worth of arguments, evidence, and speculation about what the 3I-ATLAS metadata might mean. Some of it is probably accurate, some is probably overreach. The goal of this final part isn't to tell you what to believe. It's to give you the tools to verify everything yourself, to become an independent auditor of the claims we've made and the data NASA has released. Because the only way this story resolves is if enough people check the evidence that institutions can't afford to ignore the questions. First, download the data yourself. Go to the NASA Planetary Data System, search for high-rise observations from October 2025, and locate the product ID associated with 3I-ATLAS. You'll need the exact identifier, which should be available in NASA's observation logs or through the high-rise team's public database. Download every file in the product set: the Outreach JPEG, the EDR files, the RDR files, and any associated calibration logs or metadata documents. Don't trust second-hand descriptions. Verify what files actually exist. Second, open the FITS headers. You'll need a FITS reader, freely available software that passes the file format. Tools like FITS Liberator, DS9, or Python's AstroPy library all work. Open the EDR files and examine the primary headers. Look for these critical keywords: bitpics to check bit depth, Naxis and Naxis3 to check dimensionality, filter_name or filter_ID to check which bands were captured, exposure_time to verify exposure settings, date_obus for observation time, date_created for file creation time. Write down the values. Compare them to the Outreach JPEG. Do they match? If bitpics is 16 but the JPEG is 8-bit, that's a discrepancy. If Naxis3 suggests multiplane data but only one plane exists, that's a discrepancy. Third, check extension counts. FITS files can contain multiple image extensions. The primary header should list how many extensions exist. Open the file and count them manually. Do the numbers match? If the header says 5 extensions but you only see 3, where did the other 2 go? Look for Xname keywords labeling each extension. Are they consistent with the filter keywords? If the filter keywords reference RED, BG, and NIR channels, do corresponding extensions exist? Fourth, examine calibration flags. Look for keywords like dark_subtracted, flat_fielded, radiometric_calibrated. If these are set to true, indicating corrections were applied, look for associated calibration files in the product set. Do they exist? If corrections were applied without calibration documentation, that's unusual and worth noting. Fifth, compare timestamps. Look at date_OBS, the observation time, and date_created, the file creation time. The creation time should always be after the observation time. If it's not, something is wrong with the timestamps. Check ancillary files in the product set. Do their timestamps make sense relative to the main data files? Are there any files created before the observation date? If so, document which ones and what they contain. Sixth, look for thermal or spectral keywords that shouldn't exist in a visible light camera. Search the headers for terms like thermal, radiometric, emission, or spectral calibration. If you find them, note their values. Are they populated with numbers or set to null defaults? Compare these to headers from other high-rise observations of Martian geology. Do the same keywords appear? If 3I-ATLAS has unique keywords not present in routine observations, that's significant. Seventh, check file sizes. An 8-bit image should be half the size of a 16-bit image with identical dimensions. Calculate the expected file size based on the header dimensions and bit depth. Does the actual file size match? If the file is larger than expected for 8-bit data, but smaller than expected for 16-bit, that suggests intermediate processing or compression. Document the size discrepancy. Eighth, examine B-scale and B0 values. These keywords convert raw digital numbers into physical units. Compare them between the EDR and RDR files. Did they change during processing? If so, by how much? Large changes suggest significant dynamic range compression or rescaling. Check whether the formula physical equals b-scale times digital plus b0 produces reasonable brightness values when applied to the pixel data. Ninth, look for checksums. If the files include checksum or datasum keywords, verify them. Most FITS readers can compute checksums and compare them to header values. If they don't match, the file has been modified since the checksum was created. This isn't automatically suspicious, but it's worth noting. Check whether all files in the product set have consistent checksum integrity. 10th, compare to baseline observations. Download several high-rise observations of Mars from the same time period. Parse their headers using the same method you used for 3I-ATLAS. Create a spreadsheet comparing key header values across multiple observations. Does 3I-ATLAS have unusual values, extra keywords, or missing extensions compared to the baseline? Statistical comparison tells you whether 3I-ATLAS is an outlier or typical. 11th, document everything. Take screenshots of header sections, save raw text dumps of keyword value pairs, record file sizes and timestamps, create a shareable document with your findings, upload it to a platform like GitHub, archive.org, or a public Google Drive folder. The goal is reproducibility. Anyone should be able to follow your methodology and verify your observations. 12th, check for updates. NASA archives sometimes update files after initial release, correcting errors or adding calibration data. Check whether the 3I-ATLAS product set has been modified since its original release. Archive sites like archive.org's Wayback Machine can sometimes show historical versions of files. If files have changed, document what changed and when. 13th, reach out to experts. If you find something unusual but don't know how to interpret it, ask. Post your findings on astronomy forums, email high-rise team members, or contact planetary science researchers. Most scientists are happy to explain technical details if you approach respectfully and show you've done your homework. Don't accuse, don't assume. Just present your observations and ask for clarification. 14th, know what would constitute proof. Metadata anomalies alone don't prove intentional data withholding. They're circumstantial evidence at best. Definitive proof would require one of these: an insider leak showing internal versions of the data with more detail than public releases, a FOIA request that forces release of withheld files, independent observations of 3I-ATLAS by other telescopes that contradict NASA's characterization, or a checksum verified comparison showing public files were modified after creation in ways inconsistent with routine archive maintenance. 15th, remain skeptical of all interpretations, including this one. Everything you've heard in these 15 parts is provisional. We've outlined what the metadata might mean, but might isn't does. We've suggested that discrepancies deserve explanation, but discrepancies don't automatically imply misconduct. Maintain epistemic humility. The goal isn't to prove a conspiracy. The goal is to determine whether the public record matches what was actually observed. That's a factual question, answerable through verification, not speculation. What would it take to resolve this definitively? NASA could release a technical memo explaining the 3I-ATLAS data pipeline, clarifying which metadata fields are meaningful and which are artifacts, documenting what processing decisions were made and why. That memo should explain the bit depth conversion, the absence of multiband products, the extended release timeline, and the presence of unusual calibration keywords. If such documentation exists internally, there's no scientific reason to withhold it. If it doesn't exist, that itself is a problem, suggesting the mission team didn't adequately document their procedures. Alternatively, NASA could release the complete raw dataset, all CCD channels, all calibration files, all pipeline processing logs. Let independent researchers reprocess the data using alternative techniques. If the outreach JPEG genuinely represents the best achievable result, reprocessing will confirm that. If better results are possible, researchers will demonstrate it. Either way, transparency resolves the controversy. What you can do right now is verify the claims. Don't trust us. Don't trust NASA. Don't trust Earth exists. Check the data yourself. It's public. The tools are free. The methodology is documented. If enough people independently verify that the metadata anomalies exist, institutional pressure for clarification becomes irresistible. If enough people verify that the anomalies are artifacts, the controversy deflates. Science isn't about authority. It's about evidence. The evidence for 3I-ATLAS sits in downloadable files, waiting for anyone curious enough to look. What you find might support the narrative we've outlined. It might contradict it. It might reveal entirely different anomalies we haven't considered. That's how discovery works. That's how transparency empowers verification. That's how trust gets built or lost, one independent audit at a time. The truth about 3I-ATLAS is in the data. The question is whether you'll go find it.